Now, in all cases, if the coefficients of friction are all 0, then F1 equals F2 equals 0. Remember, little f1 and little f2 were the frictional forces, magnitudes of the frictional forces. Okay, now, the net force then on the first object will be negative tension plus the parallel component of the weight. And the net force on the second object will be the tension plus the parallel component of the weight. And I'm not sure about that negative sign. Let's see, then, never mind. That's all right. Okay. Okay, now, the condition is the two accelerations are equal to 0. And from that, it follows that F net 1 over M1 equals F net 2 over M2. Let's talk about that just a little more. The accelerations are equal because these things are joined. They're joined by the string, and the acceleration of one will equal the acceleration of the other. So that since acceleration is just net force divided by mass, in each case, the net force divided by mass 1 is equal to this acceleration. Net force on mass 2 divided by mass 2 is equal to acceleration 2. So the two expressions are equal, and this gives us two expressions we can use to solve for the tension. So we can easily solve that case. Now, you would need to work through that with the given parameters of a given system, but that would be a fairly easy task. We have a simple equation with the only unknown being t, because if we know the angles of inclination and the masses, we can find the parallel components of the weight. And of course, knowing the masses, the only unknown in this equation would be the tension. Okay, now let's go to the case where the tensions are not equal to 0. So I'll say all tensions are non-zero. I'm not sure the camera's got the top of the screen there, but we get the idea. Okay, so what do we know then? Well, now here's a case where I really don't like the use of formulas. I really like the use of pictures. So if you want to say that the first normal force is m1g cosine alpha, which is kind of a knee-jerk reaction. You grab onto that formula when you see it, and believe me, I understand that. You really need to draw the triangles and understand in terms of the triangles why these normal forces are what they are. In any case, this normal force in this case will be equal and opposite to the perpendicular component of the corresponding weight force. So for the first mass, the weight is m1g, and the perpendicular component of that weight will be negative m1g cosine alpha, if you want to do that. I really prefer the circular definition, but you know, we'll reconcile that later. And Fn2 will be this. Okay? Now, what do we know about the frictional force? We know that the frictional force can't be greater than the coefficient of friction times Fn1. Now, I should probably put a subscript on the coefficient of friction to indicate the coefficient of friction on the first mass times the normal force. Now, that coefficient of friction is unspecified. I don't want to go into too much detail here. We can set up a whole logical system by which we would reason out the behavior of the system. And if we did, we'd want to specify that the force on the first mass is equal to either the coefficient of static friction times the normal force, and that would be less or equal to coefficient of static friction times the normal force, or equal to the coefficient of kinetic friction times the normal force. Now, the reason for the less than or equal is the static friction is only enough to keep the object from moving. if you only need so much force to keep the object from moving, then you're not going to use the maximum possible static friction. You're going to use whatever static friction is necessary to prevent motion. So if this is a case of static friction, we use the less than or equal. And what we have here is an upper limit on the static friction. If it's kinetic friction, though, there's no less than or equal. It's purely equal because once it's moving, it is experiencing the entire kinetic friction. Now that's something you simply have to think about and reason as you work out the problem, and we'll see examples of that. So we have this inequality, which, if we're talking kinetic friction, is actually inequality, and that's going to be mu1 times m1g cosine alpha, because that's, of course, what the net force is. And similarly, for the second force, we have a similar inequality, which, if the system's in moving, will be an inequality with the coefficient of kinetic friction. Okay, so now I've written down the parallel components of the force. That's m1g sine alpha and negative m2g cosine beta. I'm going to leave those go without comment. Again, I prefer you use a circular model to determine these coefficients or these components. But whichever model you use, make sure you're reasoning it out and not just grabbing a formula, because the formula doesn't always apply. There are many situations in which you're not going to be able to use that formula. You're going to need to use the reasoning behind the formula to analyze the problem. We'll see some of those in upcoming classes. Okay. Now, because of y equilibrium, we've set our coordinate axes so that the x-coordinate is parallel to the incline, the y-coordinate perpendicular to the incline. We've done that for the two different inclines. It's y equilibrium that implies that the normal force is equal to the perpendicular component of the weight in each case. So if we put all this together, we find that the net force on mass 1 is negative the tension on mass 1 plus the parallel component of the weight, then plus or minus the frictional force. And there's a question whether that's plus or minus. It depends completely on the situation. Again, is the velocity in this direction or this direction? Does the weight on this side, does the parallel component of the weight on this side exceed the parallel component of the weight on this side, or vice versa? All those things influence whether that frictional force is positive or negative. And a similar expression for the net force on object 2. Now, if the cord is over a light frictionless pulley, these two tensions are going to be equal. So I can erase the T1 and the T2, and I can just use T. Using the negative here because the tension on this side is in this direction, the tension on this side is in this direction. So here the tension's in the direction opposite to what we've chosen as a positive direction. Here it's in that direction. Okay. Now, down here, simply say that the weight perpendicular, which is what gives rise to the tension force, is m1g sine of 270 degrees minus alpha. And the sine of 270 degrees minus alpha is equal to the negative of the cosine of alpha. Here, a similar argument, the cosine of 270 minus alpha is equal to the sine of alpha. So that is what gives us our mg cosine alpha, m1g cosine alpha here, m2g sine alpha here with the negative on this one. And we'll address, because there's some confusion still on the relationship between the circular model and the triangle model that you are more used to, are more accustomed to. So we'll deal with that in another set of videos, but that's the way it works out with the circular model, and we'll discuss that in more detail later.